Hello, I'm Nancy Strickland from IT Mentors. This video on F# is part of a series on the Beta 2 release of Visual Studio 2010 and the .NET Framework 4. In this video, I'm going to show you something about the newest language in the .NET family, F#. I'll start with a little information on F# and on functional languages in general, and then I'll explain some of the basic syntax of the language, and of course I'll give you examples in code. And finally, I'll talk about some of the situations that F# is well suited for and some where it might not be your first choice. When you hear that Microsoft is introducing a new .NET language, you're likely to think, why? Why do we need another language since we already have several choices? If you're watching this video, you probably already know either C# or Visual Basic.NET, so the reason for adding F# to the .NET language family isn't to duplicate what can already be done with C# or VB, it's to add a functional language to .NET so that you can program targeting the CLR, the .NET Common Language Runtime, with the advantages of a functional, that's why it's called F#, a functional language. In general, a functional language is a good choice for applications that use lots of math-type functions for scientists, researchers, mathematicians, statisticians, or business apps that are function-heavy. In many cases, those people, scientists and mathematicians and such, can use a functional language directly, even though they're not trained developers. And professional developers will choose to use a functional language when they're working in those kinds of domains, those kinds of fields, or when they're doing those kinds of apps, or whenever a particular problem seems well suited to being approached using functions. The first supported version of F#, version 1.0, comes built in with Visual Studio 2010, and of course that's the IDE that we'll use in this video to look at F#. Functional programming is a style of programming that lets a programmer say what it is the program should do rather than explicitly how to do it. So it emphasizes the evaluation of expressions more than executing commands. Languages like C# and Visual Basic.NET are more procedural or imperative languages where you write code that proceeds sequentially, step by step, to transform an input into an output. But functional programming has a different emphasis. It uses functions to combine basic values and expressions. Instead of loops, it tends to use recursion, for example, and in general, it uses objects that can change state, variables, less than it uses immutable objects. So if you say that in general, functional programming, non-procedural programming, is about static relationships and objects that don't change, well, then how does a functional program accomplish anything? The function itself does calculations. It takes an input and it does calculations and it returns a result. But because the calculations are contained within the function, it has no side effects outside. And after the result is calculated and returned, it doesn't change. So for example, if you're going to calculate the sum of a series, an imperative language would use a loop with variables for an accumulator and a counter, like this top example here. And the value of both those variables would keep changing as the loop executes. But a functional language would use a function that takes an input, that could be a set with multiple values, for example, and it returns a single value without changing the input. So for example, a functional language might do something recursive that wouldn't change the input values and wouldn't have an iterator. It could be something like this example here. The function accepts two values and it recursively works its way up the inputs, which in this case have to be sequential integers from start to end, and it calls itself with a value that's one greater each time. Then when it gets to the top, when start is greater than n, it begins working down, adding the current start, which is one less each iteration, to the result returned from the previous iteration, so the final result of the function is the total. Now, of course, this is just pseudocode. It's not F#. We'll get to the actual F# syntax in a minute, but right now I just want to call your attention to how this recursive function is different from a procedural loop, even if the loop is written as a programming function, and why that matters. Both these ways of calculating a sum work. They return the right value. But the functional approach with a recursive function is different because it supports the principle of immutability. There are no changes to values or state in existing objects as this function executes. And there are no changes at all, of course, to anything that isn't part of the function. So there's no unanticipated side effects. While our procedural loop changed the value of total and also the value of I as it was executing. Now, one thing I want to make clear is that the recursive approach shown in the pseudocode here could be implemented in C# or Visual Basic or any other language that supports recursion. Functional programming is a matter of approach rather than a particular language. But some languages make it easier than others to write functionally, and F# has been designed specifically to support a functional approach. Now, if you found that recursive example a little hard to follow, certainly harder than the loop example, that's pretty normal. Most people find it at least a little harder, at least at first, to think recursion instead of loop. So what's the advantage of F# that makes it worth learning? It's what we just said, immutability and no side effects. Those are particularly useful in certain circumstances like parallel computing and concurrency. If code is being accessed in parallel, it's very important to make that code concurrency safe so that one thread won't change a value in a way that causes problems for another thread. It's also concurrency friendly because functions with no side effects, functions that are self-contained, can often be executed in any arbitrary order, and that makes it easier to parallelize them. Also, testing and debugging are generally easier in a functional program because you don't have to worry about side effects from other parts of the program that can make a function behave unexpectedly. And as you'll see when we start talking about syntax next, F# makes it easier to maintain the immutability that provides these advantages and harder to avoid it. Now let's start looking at the syntax of F#. We'll start with the simplest expression, this first one, let x equal c. This isn't an assignment, it's a binding. It permanently binds that variable, x isn't really a variable, it's called an identifier because it can't vary. It's immutable. It can never be assigned any other value. Now, one advantage to having identifiers default to mutability is that it makes it easier to write programs that are concurrency safe. There are fewer possibilities for mutable state, so there are fewer chances that the value of a variable can be changed by one thread and then cause unexpected side effects for another thread that's trying to access the same variable. Now, you could do this in C# by making a variable read-only, but you have to do it explicitly. It's not the default. Well, F# is just the reverse. Things are immutable by default, but you can explicitly make them mutable if you need to. So that's an example of how F# is designed to support immutability and to make code concurrency safe with less effort. Now, if for some reason you need to be able to assign to an identifier, you have to add another keyword, mutable, to make the identifier explicitly mutable, to make it a real variable. So I can say let mutable x equals 3 and then assign 4 to x. Now, when you assign another value to x, then you use the assignment operator, which is this left arrow here that you draw with a less than character and a hyphen. You can't set a value with a single equal sign. That's used for comparing two objects for equality. But remember, if you're going to be using mutable variables, you're avoiding one of the principles of functional programming. Now, F# can be used for regular imperative programming. It's what's called a multi-paradigm language, which means it can take a functional approach or an imperative approach or an object-oriented approach. But if you're not using a functional paradigm, I'm not sure why you'd want to use F# instead of C# or Visual Basic. Now, within a line, F# is white space tolerant in general. In other words, you could leave spaces around the equal sign or not. But of course, you can't leave space between the parts of a two-character operator like the assignment operator, the left arrow. And if you're a C or C# or C++ or Java programmer, you've noticed that there are no semicolons at the end of lines. There are a couple of other interesting things about identifiers. First of all, an identifier can be not only a primitive type or an object type, like you'd expect with regular variables, but in F#, an identifier can also be a function type or some other types that we'll see in a minute. And then second, identifiers aren't defined with a data type, but they do have a type. F# infers an identifier's type. It figures it out from what's on the right-hand side of the expression that follows it. That's kind of like how the var data type in C# works. Now, I'm just quickly calling these things to your attention now. I'll talk more about each of them a little later in this session. And one more thing. Identifiers in F# are case sensitive. They can include letters, numbers, or an underscore or an apostrophe, a single quote. They do have to start with a letter or an underscore, though. Now, this will look familiar to C and C++ programmers. This printfn value of x is %d at this point, and then x. That's how you get output. The printfn means print with a new line at the end. There's another command here, this second line, printf, which is exactly the same thing, but doesn't print a new line at the end. Now, inside the string, the part that starts with a percentage sign is a placeholder and a format specifier for the identifier that's listed outside the quoted string. So in the output for this first one, the value that's associated with x will be printed at the location where the %d is, and it'll be formatted as an integer because that's what %d means. It means integer. %s means string, and %f is float. And remember that F# is a CLR compliant language, and that means that you can use any of the .NET classes in it. So you could also put console.writeLine and in quotes put what you wanted to output. I'm going to use printfn instead in these demos because of some other things I want to show you. There's 3 syntaxes for putting commas in your programs. Multi-line comments can be enclosed in parenthesis star and then star parenthesis, and they can be nested. Then you can also get those single line C-style comments with a // and those can start at the first of a line or anywhere in a line, and they'll comment out from that point to the end of the line. And then there's also IntelliSense comments, and they start with 3 slashes. And they get shown when the user hovers over whatever's been commented. That is, whatever comes right after that comment line. So here you see an IntelliSense comment that's immediately above a let statement for the identifier WKS. Let WKS equal 52. And then the very next line here shows a user hovering their mouse above WKS and seeing that IntelliSense comment. So now they know that means weeks, the number of weeks in a year. You've probably already noticed that I never declared a type for the identifiers that I've used. But even so, F# is a strongly typed language. That is, it's one that has to know what type every identifier is, and that won't allow you to assign a value of one type to an identifier of a different type, whether that's an explicit assignment to a mutable identifier or maybe passing an identifier into a function or in some other way. So logically, in a strongly typed language, you expect to have to declare all your identifiers, right? Or else how would F# know what kind of values were okay for an identifier? Well, F# uses what's called type inference. It figures out what type an identifier should be the first time it's bound to a value or the first time a value is assigned to it. Now, the advantage of this is that you as a developer don't need to spend time declaring identifiers before they're used, or at all, anywhere, anytime. You just start using them when you need them, the first time you need to assign them or bind to them, and F# does the rest. One of the advantages of this is that your code's shorter. It's faster to write, and it takes up less space, and that, every line you save means you'll be able to see one line more of your code on a single display page, which is always handy. And it also eliminates one source of errors because the compiler will infer the type accurately, and it won't infer it until a value is assigned to it. So you can't accidentally leave a value uninitialized, for example. Some of the most common basic primitive types are here. They're pretty much what you'd expect, except for this first one, unit. Unit is something like void. It's what's returned by a function that doesn't return a value. And then bool, of course, is the Boolean, so it can only be true or false, which are keywords without quotes. You can use the logical and or not with it, with the operators that you see here, which are like those in C#. The character is a single character, and you enclose it with single quotes. Int is an integer, of course. Float is obviously a float, and string is not really a pure primitive. It's a compound type, but I just wanted to show you what it is and that you use double quotes around it. It also has, as you can see in this example, the plus sign for a concatenation operator. Now, there are other types too. There's byte and unsigned integer and a decimal type and a double and several others. I'm not going to go into those in detail here, but at the end of the video, I'll give you a reference to the F# documentation. Before I go on, let's see a quick demo of just this much that we've done so far. Now, that's not so much to demo the few little simple bits of syntax that we've seen up to now, as it is to show you how to use F# in Visual Studio 2010. I've opened Visual Studio 2010, this is the Beta 2 version of course, to its new start page. And now I'm going to create a new project, and I've selected other languages, Visual F#, and Windows. And I'm going to select an F# application, call it FS for F# Demo 1, put it right on the desktop. But before I go on, let me tell you that if I had selected the F# tutorial project, it creates a project for you that has lots of sample code to show you the basics of F# in code that you can then run, or you can step through with your debugger and study. But we're not going to do that now. We're just going to start a simple program of our own. This is FS Demo 1. Now, the first thing I want you to notice in the Solution Explorer is that if I expand references over here, there's a reference to the F#.core, and that was added automatically when I selected F# as the project language. Now, if I want to use a namespace, the command is open, so I'll add open system. Right here at the top of the file, no punctuation ends the line. Now first, let me just show you that this is a .NET language. It can use classes from the CLR. So I'm going to add some pure .NET code. Here it is, hello world. Again, no punctuation at the end of the line, so I'll just run it. In this case, I'm going to run it without debugging, and that's so that that output will stay on the screen for you to see it, because that automatically adds that press any key to continue thing. Now, that looks like plain old .NET, and it is, but notice that if I hover over this right line here, the documentation that I get is F# documentation. I can see some of the overloads, and I can see that the return value from each of them is unit, which means, void, no value. And I can also see, let me put this back in, what argument type the overloads take, of course. Now, before I go on, I want to call your attention to this. I only have 2 lines of code on the screen, and that's all I need for Hello World. If I were writing C# or Visual Basic, there'd be a lot more overhead code. There'd be a namespace and a class and a main method and braces or end statements. So you can see that relative to that, F# is fast and simple and clean to write, and for that matter to read. Now let's see what happens if I try to use another .NET function. I'm going to use, read key. Now notice that blue wavy line there. If I hover over it, I can see that the problem is that this call returns a value, and I haven't done anything with that value. The previous call, right line, it just returned unit, so that wasn't a problem. But here I'm getting a warning, and it is just a warning. I can run without it. In fact, let me just run it here. I'm going to run it with debugging now. I couldn't before because it wouldn't stay on the screen, but now it will. It's sitting there with that read key waiting for me to press a key. But if I want to fix that wavy blue line, here's how. I could either bind the output using let, right, to a junk variable of some kind, and then I won't do anything with it. You can see that took care of my wavy blue line. Or I could just pipe the output from the function to ignore, and I haven't yet talked about pipe. We'll talk about it more later. But ignore, piping something to ignore, is like sending the output to null. Now, this pipe symbol you see is a standard pipe followed by the greater than character, and as I say, I'll talk more about it later. And again, that's enough to keep F# happy, and I don't get that warning, that wavy blue line, because it just wants to know that I'm doing something with the output. I'm going to do that so you can see how it looks. Okay. Now what I want to do is to start working with some data. So I'll start with just simple. We'll bind the identifier x to the value 3. Now, to show the mutability issue, I'm going to try to change that value. I'm going to try to use the arrow to assign something to x. And you can see that I immediately get a warning down, not a warning, an error down here. This value is not mutable. Now, I can fix that if I changed the identifier to mutable, and you see that got rid of my warning. The error line's gone. Again, we don't normally want to do that because the point of F# is to work well as a functional language, and so we try to keep mutability down a little bit. Now let's add some output. I'll do a print with a new line and say the value of x is %d. There's my format specifier, and there's x, the value that's going to go into it. I'm going to run it. To keep it on the screen again, I'm going to run it without debugging. And there we go. The value of x is 3. Now let's look quickly at how indentation for line continuation works. Watch when I press enter, and then I'm going to move the string in the print line statement to the next line at the same indentation. See the complaint that I'm getting? This value is not a function, so I can't just put a string there, of course. But if I just indent it any amount at all, then my error's gone. Now, there's no real reason to use indentation here, of course. It's just there for clarity in certain situations, and we'll see it more later in the next demo we do. Now, using indentation like this to show that a line belongs to the line above it is part of what's called the light syntax for F#. And as you can see, it's the default in Visual Studio 2010. I didn't have to do anything special to make it use that. The light syntax is simplified, and it's the most commonly used syntax option. Now, before I go back to the slides, I want to show you that there's a couple of other ways to run F#. You can run it, for example, from a console window. So let me just open that. I'll go to a command prompt there. And now what I'm going to do is change to where my F# is stored, and that's Program Files, Microsoft F# version 4.0. Oops. And now I'm going to type FSI, and that opens up my prompt. That FSI stands for F# Interactive, and so now I've got my interactive prompt there. What I can do here is enter commands followed by a double semicolon, and then I can see their effect immediately. So you can see that for certain kinds of meta commands like getting help, you put a hash mark in front, and all the commands have 2 semicolons to show it's the end of them. So let me just start with a very simple let. I've got let at x equals 3, but because I'm doing it in FSI interactively, I have to put 2 semicolons after it. And the output that I get tells me that it has gotten the type of x, it's figured out what type it is, that it's an integer type. Now I'm going to talk more about why it's an integer later, and that the value of it is 3. Now, when I was working in Visual Studio, I wrote programs with multiple lines, and I ran the whole program at once. And I can do that from the command line too, but to do that I'll have to write a script and then run the script from the command line. So to do that, I'm going to get out of the F# prompt. And remember, for these commands that manage F# interactive, that manage the FSI programs, not commands in F# themselves, for the commands to the FSI, I start with the hash mark. And so this is the command to get out, which is quit, again followed by the double semicolon. Now that puts me back at my DOS prompt. And so here I'm going to type notepad test FSX, and that's going to create a little text file for me with the extension FSX. And when I do it, it says, do I want to create a new file? Yes, I do. I'll just put a couple of lines in it. We'll let x equal 53 here. I'm going to run it in FSI, so I need the 2 semicolons. I'll let y equal x minus 11, a couple of semicolons again, and then we'll do a print. Oops. And I'll print out what y is. Now I'm going to save it. And now I'll close it. I just did the default save, so it should be right here in my current directory. And there it is, test.fsx. And then to run it, I type FSI, and then the name of it, test.fsx. And you can see that FSX is the standard extension for F# text files like this, F# scripts. And it will print out the answer, 53 minus 11 is 42. And now I'm going to exit from the command prompt to show you something that's kind of similar to working from the command line, but inside of Visual Studio 2010, and that's the interactive window, another way to run F#. Now I'm back in Visual Studio, and I'm going to hit Control-Alt-F. This is the F# interactive window. See it down here on the tab? And it's a new window in Visual Studio 2010 that's there to support F#. Now, it's pretty much the same as what we just saw in the console. See, in fact, how the prompt is the same here? And I use the same syntax with that double semicolon terminator. So let me type in the same thing here. Let x equal 3 semicolon semicolon. And look, there's the same output that we saw from the command window. It shows that a value has been set and what type it is and what the value is. Now, another thing that this window can do in Visual Studio, besides duplicating the command line, is to immediately execute any selected line or lines from your main code editing window. For example, if I select these 3 lines, let me change X to make it mutable. And then assign to it. And what I'm going to do now is select those 3 lines. Then I can right-click, for example, and choose Send to Interactive. And then this is done down here for me. So it says the value, it prints out the answer here. The value of x is 4. That's the correct output. And then it also gives me a line similar to this one. It says x is mutable, and it is an integer, and the value of that integer is 4. And I can do the same thing, I'll do it again here, without having to right-click by pressing Alt-Enter, and that just gave me the same output right there. So that's a quick way to execute a tiny little bit of code and see what it does. Okay, so that was a general introduction to the mechanics of using F# in Visual Studio and in the console. And now let's learn some more syntax. Here are the most important or most common collections in F#. Lists, arrays, and dictionaries are pretty similar to what they are in other .NET languages, and then there's also tuples and sequences, which I'll explain. A list is a collection which is defined in the namespace for Microsoft F# collections, and like other collections it has properties like length and methods that we'll see later. It's an immutable linked list, and the values in it must all be of the same type. And of course F# will infer what that type is for you. The first line here shows binding an empty list to an identifier. You see that it uses square brackets. And then the second line binds a populated list to an identifier. Notice that the values are separated by semicolons and the whole list is inside square brackets. And the next line is an example of a list that is automatically populated with sequential integers. So this list will be 1, 2, 3, 4, 5. You can concatenate two lists and then bind them to a third identifier with the @ symbol. That's the concatenation symbol for lists. To access a specific value from a list, you use a dot after the identifier for the list and then brackets around the index of the item you want. The index is 0 based, so this example gets the second value in the list. And then finally, the last line shows you how to print a whole list at once using %A, which stands for anything, as your placeholder and format specifier. Arrays are native mutable arrays. They're delimited by bracket and pipes with semicolon separated values like you see here in the first line. So that's a bracket and then a pipe, the values, and then a pipe and then a bracket. And then the second line creates an array of 3 items, and each of those is initialized to 0. And the last line is changing the value in the first item of an array. Notice that we've got that dot plus bracket notation and then the right arrow to do the assignment. Dictionaries in F# are like dictionaries in other .NET languages. You create them with semicolon separated pairs of comma separated keys and values, like you see here in that first line. And the whole dictionary is enclosed again in square brackets. Keys and values can be of any type, and not just primitive types, even lists or arrays even, but keys have to be of a consistent type, and so do values, and keys of course have to be unique. Now you retrieve a value like it shows in the second line, again with that dot plus brackets notation. A tuple, or a tuple, apparently how you pronounce it depends on where you're from and what your background is. I understand that tuple might be more popular with Python programmers and tuple with mathematicians. I don't know. I'm going to say tuple, but if you go with tuple, you're going to get no argument from me. A tuple is a collection of objects that can be of different types. You create a tuple with parentheses and comma separated values or identifiers, like this first line shows here. So we've got some values of different types, and then at the end that X is an identifier. You can assign 2 values, or 3 or 4. You can assign multiple values to a tuple all at once. Now that tuple is now unnamed, but each of the variables in it has a value. You can get values back out of a tuple, but you have to get them all at once. You can't use more or fewer identifiers to retrieve the tuple data than there are items in the tuple. So if my tuple has 4 values, you have to retrieve 4 values, like it shows here in the next line. To print the whole tuple is similar to printing a list. You use that %A. A sequence, which in code is SEQ, holds a sequence of items like a list. The syntax for a sequence is to enclose it in curly braces. So it's like a list, but it's different in that only one value is in memory at any one time, not the whole list. This shows here how to create one, so I've created a sequence of 1, 2, 3, 4, 5. Sequences can be, and often are, much longer than this because only one value is in memory at any one time. So it's very common to have a sequence whose length isn't even known at compile time. For example, a sequence can be set up to hold all the words in a text file that's going to be specified at runtime, so the number of words in it isn't known at compilation. And that means you can work on only one value at a time, the one that's currently in memory, which of course is a drawback of using a sequence, but on the positive side, using a sequence requires fewer resources, less memory, than another collection like a list. So typically the nature of a sequence is that you'll be iterating through its values and performing some action, and I'm going to show you how to do that next. Collections have built-in methods, functions, that do many of the standard things that you'll want to do in a functional program. These are a few of the common ones. Map, for example, when you use map with a collection, it's followed by a function that will be applied to each element of the collection, and then it returns those as a new collection. So in the example, you see that there's a list, which is the numbers 1 through 3, and there's a function named square, which is going to be mapped to each of those in turn. So that'll assign to the identifier squares, SQRS, the values 1, 4, 9. And of course, the original values will not be changed. They're immutable. And then sum, well, obviously it sums up the collection and returns that value, so this would return 6 here. And iter iterates through a collection applying a function, but it returns the type unit, which is nothing, void, right? Since it doesn't return anything, the function you use must have a side effect that's the whole reason for using it. For example, if I say let print int x equal print %dx, then if I say list iter print int, it's going to print each of those integers which will be passed into it. And we'll see more about how to use these a little later in this video. There's also quite a few other functions that collections have, like sort by and find, but I'm not going to go over all of them here. I'm giving you a link to the official F# documentation in the resources at the end of this video so you can see all of them. Conditionals are pretty simple. You see the if and the else if, which is elif here, and the final else. The spacing, the line breaks here, is a little arbitrary and flexible. The indentation of the printfn lines is required because they're a continuation of the previous line, but they could also be written directly after the then or the else on a single line. And that if, elif, and else could be written on a single line or different like it is here for better readability. One important thing that's different about if statements in F# is that they return a value, and that value is the last value processed within the statement. So this second example here, returning a value, would put a floor of 0 on the value returned by the conditional statement because it would return a number. If it were greater than 0, right, it would return x. But if the number were less than 0 or 0, it would return 0. So the printfn statement here that we're looking at would print 0 because x is negative. We'll see more about this in a minute when we start talking about functions. And here's a little for loop. You can see that it's most like a for each loop. It takes a list as its second argument after the n, and it iterates the number of times there are items in the list. And in each iteration, the identifier I takes on each of those values one by one. Now notice the do here, and that the second line, the printf line, needs to be indented. The list doesn't have to be literally in the for loop. It can be an identifier, like in the second item here. If you should have multiple lines in your loop, indent each one the same, and then the first unindented line shows the end of the loop. Then the third example shows generating a list with a for loop. In this case, we're creating a list of tuples, with the first value being a number from 0 to 10. Notice that the list includes both end values, and the second is the square of that number. And it also shows you here that right arrow operator, which means return. So we're saying for each number in the list, return the number itself and its square as a tuple, that is, comma separated inside parentheses. Now, F# is a functional language, and one of the things that means is that functions are very much like any other value in that I can bind a function to an identifier just as if it were a value. So that's what I'm doing here. Let doubler x equals x times 2. And then I can use that function, doubler, like it shows here in the next line, assigning its return value to another identifier. So then num will be 10. And I can also use it like in this next line, just printing out the output. And then there's another example here to show you that with two parameters, you leave a space, not a comma, between those parameters. I could also write this so that the two parameters are passed in as a tuple, like in the next example, which of course means that they're actually a single parameter, which is a collection of two values. So when I pass those values in, they have to be parenthesized and comma separated. Now remember that F# has to infer types for parameters and also return type for the function itself. So in the case of this adder function here, it infers that the inputs are integers, so the output will be 2. Now you might be wondering how or why F# decided to infer that these values, the parameters to adder here, were integers, because that plus operator could apply to integers or to floats or to doubles or to strings. Well, the reason that F# chose integers in this case is that integer is just set up as its default choice. But for this function, again, there's really no reason that the arguments couldn't be something else. So if you want to tell F# to type the input parameters as floats, you can specify the type by following the identifier with a colon and a type, like it shows here in this second line, and then parenthesize it. Now remember that when you use it with printf, like in the third line here, you also have to change the format string from %d to %f. And also, you'll need to specify the two arguments to adder with a space between them and parenthesize that whole call to adder so that that adder function happens first, and then it's the third argument to the printf function. Now you could do the same thing with strings, since the plus operator is also the concatenation operator. So here in this next example, the argument is set up as a tuple, so I'm calling it with a tuple of strings. Or there's another way. I could also use an apostrophe in front of the identifier name. That's this fourth category here, generic type. And that the apostrophe in front of the identifier name means that the identifier is generic. And so it could be bound to any data type. So I'm saying X can be any data type, Y can be any data type. That's what that apostrophe A means. So if I say it's generic, then F# won't try to infer a type until runtime, when it can see what type is passed in as X. Now this is really helpful because you can now call it any way you want with integers or floats or strings. But of course, after the compiler has inferred a type at runtime, you have to continue to use that type. In other words, just because I've used this apostrophe A to say the types are generic, I can't call it once with floats and then again with strings. After it has been called the first time and F# has made its decision about what type it is, it's going to continue to have that type throughout that run. Here's a multi-line function. It's bound to an identifier, func1, and there's several things I want to show you here. First, I've got for I in 5.5.20. Now, the first 5 is the start value, and the 20 is the end value for that loop. And the second 5, the one in the middle, is the number I want to increment by each time through the loop. So this will count by 5s from 5 to 20. And then the printf here, which keeps the output on the same line. It's not printfn, it's printf, so there's no new line. It's got extra spaces between the %d, the placeholder, and the quote that's the end of that string, so it'll print each item with spaces in between. Now, it's a convention that you start a new line after the equals in the let line, because that makes the body of the function separate from the identifier. And of course, every line that's part of the function is indented. So there's two lines to this function, the for loop and the printfn. Now, the first printf is indented even more to show that it belongs to the for loop. And also notice that there's no explicit return line that's part of a function. The value of the last statement executed is the value, or the last expression evaluated, is the value that the function returns. So this function returns unit, nothing. And actually, we don't care what the function returns because it's a side effect of the function, the printing, that we care about. But printfn, the last statement executed, the last function returned unit, returned nothing. So that's what this whole function, func1, returns. Now the next little example there is a function that returns a value. So you can see that I've got func2 n, meaning it takes an argument, that n. It has a conditional if n mod 2, and you know that that means divide n by 2 and return the remainder. So if the remainder of whatever we pass in divided by 2 is 0, it's an even number. So I want to return the value even, and I just put then even. I'm not using a keyword like print or anything before the even, or on the next line the odd. It just says else odd, because if I just put the strings there, they'll be the last thing evaluated in their branch of the if, and that will make them, either even or odd, the return value from the function. And then this last line here, the one that's not indented, the printfn, it's not part of the function because it's not indented. And it shows how you call it. So you'll say printfn, and then %s, because the return value is a string, either even or odd. And then we're calling func2 and sending it 5 as the argument. Now, because it takes an argument, I've parenthesized it to show that the function with the argument is called first, and then its return value is what's passed to the printfn function. Now, you can also return multiple values for a function if you return a tuple. So that's this last example here. We say let's switch them x, y, we're passing it a tuple, equals y, x. So the return value from this switch 'em function is the input values reversed. So this printfn line here, going to take as an argument switch them with 2, 5, and what's going to print out is the tuple 5, 2. Now again, we had to parenthesize switch them, the whole switch them 2, 5 to show do that function first. The 2, 5 within it had to be parenthesized separately to show it's a tuple. And then that %a says that the format is just anything, so it will print the tuple. Now, I think that these two last lines here is a good example of how efficient F# can be. Isn't this amazingly easier than a procedural switch function where you have to store one value in a temporary variable and then move the other two variables around and then get it back from the temporary? This is a lot simpler, and it's simpler because you're sort of telling F# what to do to switch them, but not how. I've already opened a new blank F# project here, and I'm going to start by typing in the doubler function. Now, if I hover my mouse over the name of the function doubler, you can see that F# has inferred that it accepts an integer and returns an integer. Now, here's another one, adder. It accepts 2 arguments, and let me hover over it, and you can see integer, integer, returning an integer. And now I'm going to modify adder so that what it takes is a tuple. And to do that, I just had to add parentheses and a comma. And when I hover over it this time, you can see int star int, returning an int, and the star here, of course, doesn't mean multiply. It's the divider between the inferred types of the elements in a tuple. Now, I want to make the first parameter a string. I'm going to use that syntax that allows me to specify the type instead of having it default to integer. Now I'm going to hover over adder again, and you can see that I didn't have to specify that y was a string. F# figured out that it had to be a string too. If x is a string, then y has to be a string, and the return value also has to be a string, and therefore the operation is going to be concatenation. Now let me change the first parameter here to a generic. Remember, that's the apostrophe, and it's a by convention, although it could be something else. Now I'm going to hover over it again, and you can see that it's used the default type integer, but then I can call it with floats. I'm going to come down here and call it with floats. And if I hover over adder in this case, it has now figured out that the types have to be floats. And it also knows that up here, right? Higher up as well. Now see this blue wavy line under 3.2? Now if I hover over it, it tells you that the fact that I used a float there has constrained the type of that function's parameters to floats, which is true, and in fact it's what I wanted to do. Now remember switch 'em. Here's how you could use it. First I'll set it up. Let's switch 'em xy equals yx. And now I'm going to run it, and I'll print out the results. The capital A for anything. Switch them, and I'll use a 3 and a 5. And I'm parenthesizing the switch 'em itself so that, oh, I forgot to call that switch 'em. There we go. Now I'll get rid of that red wavy line there. I had to parenthesize that so that it would, do that function and take the return value for it and make that the argument to the print. Now I'm going to declare a tuple. And use it as the argument to that function. And then I'm going to get the values back out of the tuple like this. See how I can assign both of those at once, val 1 and val 2? In fact, I have to do it that way. I'll get an error if I have too few or too many identifiers on the left of the equal signs. It has to be just enough to exactly hold the number of variables that are in that tuple. Or I guess I should say the number of values that are in that tuple. And now I'm going to print out the first value in that reverse tuple just to show that everything works correctly. And I ran it, but it got off the screen too fast. I forgot to do Control F5 to run without debugging. And there we go. So the result of the first switch there with the hard-coded 3.5 when I printed it out right here. Oops. When I printed it out right here was 5.3. Then I used a tuple as the argument to switch them, and then took the result and put the results in tuple 2. Then took tuple 2 and assigned its two values to value 1 and 2. And when I printed out value 1, it was, of course, the revised value, the 5. As a functional language, F# supports many features that make functions more functional, more useful. And we're going to look at each of these next. F# supports lambda functions, which are relatively small, unnamed functions which are written in line. So, for example, if I need to multiply a list of values by 3.5, I might write a separate named function and then map it to the list. But since this is a very short, simple function that I don't think I'm likely to need to use again, then it might not be worth the overhead of writing it as a separate function. So instead, I'm going to write it right here as a lambda function, like this first line. I've got fun x, which means it's a function of x, and that function of x returns x plus 1. So that parenthesized expression starts with the keyword fun, followed by the identifier or identifiers that are inputs to the function, followed by a right arrow, followed by the body of the function. Now, normally the body is very short, really just an expression that the function will return normally. So then I can use the lambda wherever I would normally use a named function. For example, remember that after map, you provide a function to be applied to each element of a collection. So in this example, I'm going to add 1 to each element in the list of numbers from 1 to 10. So I say map, and then instead of the name of the function, instead of referring to a function that adds 1, I've just used a lambda. So I've written the function in line, in place. And in the case of a short little function like this, it makes my code shorter and simpler to read than if I'd written a separate function in some other location and then called it here. Now again, the purpose of this is simplicity. So it's the developer's judgment call about when a lambda is a better choice than a separate standing full function. Curried functions are functions that call another function and provide one or more parameters to that other function as a default. So a curried function lets you call that other function a little more simply by providing only the non-default parameters. So suppose I have this function here, add nums, that will add any two numbers. If I find that for some reason I often need this to add 3 to a number, I could curry a new function like it shows here, where I say let add 3, that's the curried function, equal add nums 3. Now you can only curry from left to right, so that means when I call the function add 3, F# will call the function add nums with 3 as the first parameter, and then with whatever parameter I pass to add 3, that'll be the second parameter that's passed to add num. So when I say let result equals add 3 4, the 4 at the add 3 turns into add nums 3, and then the 4 is that second argument, so it ends up calling add nums 3 4, and the result is 7. Higher order functions are those that take another function as an argument. Actually, we saw this before with printfn, where we sent adder 52 to printfn as one of its arguments. There's another example down here where we expand, sort of an expansion on the first one I just did, where adder itself is taking a function, doubler, as an argument. So what gets printed here, we call doubler 5 first, it returns 10. We call adder then with 5 and 10, it returns 15, and what gets printed is 15. Now the map function that we use with collections, right, is another example of a higher order function. Its first argument is a function that's going to be applied to each element of the collection. So here I've got x equaling the integers from 1 to 4, and map is going to take doubler and map it to x, so it'll return 2 4 6 8. This ability to compose functions together means that many small building blocks of little functions can be combined to create very complex behavior, and this higher order functions is a critical part of functional programming. Along with immutability, it's one of what you might call the foundation principles of functional programming. A recursive function calls itself just like it does in any other programming language. In F#, though, functions can only be used recursively if they include the REC keyword. Now that's different from most programming languages where you don't have to do anything special to make a function recurse. You just call it, or let it call itself. Now the classic recursive example is of course the Fibonacci series, which is what it shows here. A nested function is defined and used in, it's fully included within, and it's scoped to another function. You can nest functions to build more complex functions, like in this example here. Here we have a function, func3, that takes a tuple, but the first value of that tuple can't be greater than 10. So, and if it is, we just want to set it to 10, let's say. So there's a little nested function, setMax here, that checks to see if its argument, x, is greater than 10, and if so, it returns 10. Otherwise, it returns whatever that number was. Now remember that an if returns a value, so that's how this is working. So these first 3 lines here define the setMax function, and then the next line calls setMax on a, which was that value that was passed in as the first part of a tuple to func3. And then the result of calling setMax on a is assigned to c, and then the return from the whole function is cb instead of ab. Then, so if I called func3 here in this example, if I called func3 with the values 16 and 22, and I'm going to print it out with that %a, the output will be 10 and 22 because it checked that first function, it was greater than 10, reset it to 10, and returned that new value. Now, the nested function, the setMax, the one that's inside, is scoped to the outer function. So outside the contents of the func3 function, the setMax function doesn't exist. So it's a little like a Lambda function, but it's named. And one reason for naming it is if it needs to be used multiple times within that outer function, if that outer function is large, which we'll see an example of in just a minute, then it makes sense to name it and just call the name each time you need it. Pipelines move the output from one function to the input of another with the pipe operator, which is a standard pipe character followed by a greater than symbol in F#. So here I'm declaring a list of 5 floats here, and I'm then setting up a function that returns 110% of whatever is input to. And then I'm using a pipeline to send vals, the original input, to the list map function, which will return a list of new values that I'll store in the new vals identifier. Or here's another example down here, a multi-line function with a nested function that uses a pipeline to return to raise a number to the 4th power. And this is also the example I was talking about of why you might prefer to use a named nested function instead of a lambda. If the function has to be used more than once inside the containing function, then it's shorter to name it and just use the name instead of writing the function body out each time you need it. And of course, obviously, it's also less error prone. Pattern matching is something like a switch or case statement in other programming languages. It tests a value against a whole series of conditions, and each case in a pattern has a return value. So if I call getClass here, the identifier here, with the argument 2, it would return the string sophomore. Now, the last thing here, the underscore, is the default pattern. It's there to catch all of the possibilities. So when you use an underscore, you're saying if it's not a 1 and it's not a 2, return the word error. And as you'd probably assume, it has to be the last value in your pattern matching statement. Now, there is also another shorter syntax for this that you see. You leave off the argument to the function getClass, and you substitute the word function for that match x with line. And then F# infers that you're matching whatever argument is passed into the getClass function against either 1 or 2 or something else. Now, that also lets it infer that the type of the argument has to be an integer, but you don't have to use an integer argument in pattern matching. It could be a string, for example. And then discriminated union. This creates a new named data type that can have only a limited specified number of values. It's something like an enumeration. So if I create a new data type called classification that can have these 4 values, then I can assign those values to a variable. I can say let x equal freshman, again without quotes, because it's one of my values in my discriminated union. So after this let statement is executed, then F# infers that the type of x is classification. I'll show you an example of using a discriminated union in the next demo. Now I've got a few examples of using functions from Microsoft for you. They can be downloaded from the link that I'll give you in the resources page. They're longer, so I've already pasted them into a new solution, and we'll talk about how they work and then run them. So let's look at this. The first thing you'll notice is that function sample2 explicitly shows here that it takes no arguments. It does that by putting empty parentheses after the name of the function where the argument would normally go. Those empty parentheses are a way to write out the unit value, which remember is void. You could leave them out just as well, but they're here just so you can see that this syntax is sometimes used again to make it explicit. Then the next 5 lines here inside the function are nested functions. The first returns a Boolean value here that is going to be true if the value passed to it is even. That is, if it has no remainder when it's divided by 2. I'm sure you recognize the % character here as the modular operator that returns the remainder when n is divided by 2. And this single equal sign here between the n%2 and the 0 is the Boolean comparison operator for equality. It's not an assignment because, it's not a link to an identifier because it doesn't have a let, and it's not an assignment because the assignment would require that arrow that faces left, and also it'd have to be mutable. Then the next 2 functions here, the tick and the talk, are followed by they print the word tick or talk followed by the number that's passed into the function. So tick will be followed by a number, and then it will print tick and that number, and talk does the same thing. And then this next function, this choose function, takes 4 arguments. The first 3, f, g, and h, are all functions. So choose is a higher order function. A function, in other words, that takes functions as its argument. And then the fourth thing passed in here, x, is a value. Now you can see that this first one, f, must be a Boolean because it says if f of x. F is some function of x. So if it's true, then we will do function g. That's the second argument. And again, the second argument to choose, and the argument it takes is the same x that's passed in as the fourth value. And then otherwise, we'll do h, the third. Now the next function, tick-tock, calls choose. This is actually a curried function, right? Because tick-tock is calling choose and providing it with 3 of the 4 arguments that it takes. So what choose is going to do, it's going to check to see if the even function up here returns true for whatever number is passed to it to choose as that fourth argument. And then if so, it will call tick for that fourth argument, and otherwise it will call tock for that fourth argument. In other words, choose still needs a fourth argument. If that argument is even, it'll call tick. Otherwise, it'll call tock. Now, tick-tock sort of encapsulates that logic simply. So here, I'm going to call tick-tock with I for I equals 0 to 10. Now, when tick-tock is called with I is actually going to be passed to choose as its fourth argument. So basically, for each of these numbers, tick-tock I will say if that number is, we'll use choose to say if that number is even, print tick plus that number, otherwise print tock plus that number, because that's what the tick and tock functions do. And so there's my function defined up to there, because all those lines are indented under my function. And then here, I'm calling that function. Function sample 2 is the name of it. It is, again, being called without any argument, so I've got that thing there to show the unit argument. And then I'm piping it over. Here's the pipe symbol right here. Oops. Have to be careful with that. I'm piping it to ignore. Remember that keeps me from getting complaints. Okay, I'm going to run it now. I used Control F5 to keep it on the screen, and there it goes. Tick tock, tick tock, tick tock, depending, tick if the value is even and tock if it's not. And so from 0 to 10, it prints out those numbers. Press any key to continue. Now I'm going to comment this out and just move down a little ways and uncomment this to show you another version of tick-tock. It's got the same functionality, but it uses a lambda. Okay, so what we've got here, first of all, let me just show you, I guess it's obvious, that it's shorter and looks like it might be a little simpler to understand. I didn't have to write 2 functions. I didn't have to write even, because I've got that as a lambda. I'll show you in a minute. And I also didn't use tick-tock. So let's see how that works. I've got the tick function, it's the same, and the tock function, and the choose is the same. But then for I equals 1 to 10 do, I've got inside choose, I've got my lambda function just written directly in there. And that's a lambda for even. So instead of using the function even and then making someone go and look and say, what is even? I've just got it written right in there. Function in, and it takes the in mod 2 and checks to see if that value is 0. So that's the even function, returns true or false. And then I've got tick and tock written right there, and then I've got the I written there. So same kind of thing basically, and I'm going to run it now. And of course the functionality is exactly the same. The point is to look at how you can simplify a function by using things like lambdas in place. I also simplified it in this case by not currying using that tick-tock. And curried functions can be useful in certain situations when you have to call a function repeatedly with the same arguments, and in other cases they just make needless extra complexity. And now I have one more example here. Let me uncomment that. And it's here because it uses some pattern matching and also some .NET functionality. It uses the date time class that has an enumeration for the days of the week and also has a now function to find out what today is. So because I need that, I'm going to start this with open system. And then the next thing I have is a discriminated union here. Actually, that doesn't need to be indented like that, although it doesn't hurt. Okay, so this is a discriminated union. The name of it is hours, and it can take on two values, either some or none. And some is a tuple of two integers. And then the next thing we have here is a function definition. And you can see that it's a nested function. The nested function is called opening hours, and it takes an argument called day, and it tries to match a day. And then here are values from that enumeration from my date class, day of week.Monday, day of week.Tuesday, Thursday, Friday, or Wednesday. And then here's the default value, so that would be a Saturday and Sunday, because they're the only ones that aren't included here. Now you can see that these first three values do not have a right arrow after them, so they're fall-through values. In other words, if the day is either Monday or Tuesday or Thursday, the return from this pattern matching is going to be the same as that of Friday. This sum, 1719, applies to all of these four here. And then if the day of the week is Wednesday, it returns sum 919. Remember, sum has to have a tuple, so there they are. And then for any other day, that's Saturday and Sunday, what it returns is none. Now, actually, this would be a good time to tell you what it is that this function does. I didn't mention that, did I? It checks today's date, and depending on what it checks today's date to find what day of the week it is, and depending on what day of the week it is, returns the opening hour for a shop. And every day, Monday, Tuesday, Thursday, and Friday, those opening hours are from 9 in the morning till 5 p.m. If it's Wednesday, it's from 9 in the morning till 7 p.m. Stays open till later hours on Wednesday. And if it's Saturday or Sunday, there are no opening hours. It's closed. Okay, so that's what that function figures out for you. And then we have an assignment here, not an assignment, I'm sorry, linking, a binding of a value to this today identifier. And that value, is the day of the week from the date time class in the .NET framework. So we're using the framework here. And so it finds, gets now and figures out what day of the week it is and assigns it to today. And then I'm going to do another pattern matching. I'm going to use this function. This function is this argument here with today passed to it. So whatever day today is, like let's say it's, Friday, then Friday is what's going to be passed to opening hours. And so that becomes day, and then we match that day value with one of those days of the week. Okay, then we're calling this nested function in another match, and if what's returned from this is either going to be sum plus a tuple, or it's going to be none. That's the return value from this nested function right here. So when we do that nested function, if it's none, if what's returned is none, then we're going to print the shop is not open today. And if it's sum with a tuple, some particular tuple, then we're going to print the shop's open today from, now this tuple we're going to call the first value S and the second F. So here's the S and F being sent to that printf. And I've got a %D here to hold them. Now, see that :00, that just means that after you print the value of S here, you immediately print a :00 after it. And when you print the F here, you print the :00 immediately after that. And that's nothing but a dash right in between them. And then this O2 here says when you format this integer, this F, format it with 2 places, even if it only has one. In other words, precede it with a 0 if it only has one digit. If it has two digits, if it's 11 or 12, then the 0 doesn't come in. And that's it. It's kind of a nice, short, simple program. It's, about 20 lines or so. It would certainly be longer in either C# or Visual Basic. Let me run it. Okay, the shop is open today from 9 hours to 17 hours because, as it happens, today is a Monday. Now, let me remind you that all three of these examples are available from Microsoft at the URLs that I'll give you in just a minute on the slide that has resources for more information on F#. Okay, how about some of the situations where functional programming can be especially useful, situations where F# can be a better language choice? The first area is technical and quantitative computing situations where you have a lot of numbers to crunch. That can be simulations, for example, or data mining or something. And then language-oriented programming, like writing a custom parser for a particular domain-specific language. And then, as we've said before, parallel programming and concurrency. Now, there's also areas where F# isn't usually the best choice. For example, F# in version 1.0 doesn't provide any code generators. So you can't use a simple graphic tool to write Windows Forms, for example. So if you want to create a user interface, you're going to want to use C# or Visual Basic and then just interoperate with F#, which isn't a problem because they're all CLR compatible, so they interoperate easily. The function part of your app can be written in F# and the user interface in another language. Also, if you're writing heavy object orientation, where you're working with object hierarchies, maybe doing polymorphism, you can do this with F#, but that's not really its strength. Now, I've barely gotten started with F#. Obviously, there's lots more. This video isn't really intended to cover F#. It's just an introduction to F# and especially to how to use it with Visual Studio 2010 and how Visual Studio 2010 supports it with new features like the interactive window that we saw. So here are some more resources to review what I've done in this video and take you further and deeper into F#. Obviously, you already know that you can get F# when you download the Beta 2 of Visual Studio 2010 from this first link on MSDN. There's also a matching F# for VS 2008 that you can get a link to from the Microsoft F# Developer Centers, which is the second link here, and it's also got links to formal documentation and training material, like articles and videos and chapters from books. There are some good blogs that can be helpful too. The first is the F# team at Microsoft. The second is a forum for F#. And then I've got Don Symes' blog. He was the lead designer of F#. And then you can download some great F# samples, including some of the demos that I've shown here from this last link. Now, the source code for my demos from this video and others are on my blog at the URL shown here, and I'm announcing it on Twitter as new videos are posted. So if you'd like to know what's available and when, follow me on Twitter at nstrickland1. And that's it for this session. Thanks for watching. Bye-bye.